Okay. Thanks everyone for joining me today. What I'm going to be, my name's Kyle Bosler-Reeder, first of all. I'm at the University of Nevada, Reno. I'm a second-year master's student. And what I'm going to be presenting today is a gravity model I created last year, which is first part of my thesis. So the reason I created a gravity model is my thesis is to try to attain a convergent joint optimization. And in this case, what we're looking at is P-wave first arrival data and vertical component gravity data. So what we have is a seismic inversion that's in place, working with a company called Optum, and we have a seismic model that I put together. What we needed is a gravity model that was compatible with our seismic model. So first we kind of looked at what our options were. You may be familiar with GMSys or Grav3D. These are kind of popular, somewhat commercial products. Those, we weren't able to really get in and get the algorithms out of those, so we had to look elsewhere. We looked at Gaussian quadrature. This can provide an arbitrary level of precision, but it's not very efficient. And we're doing Monte Carlo, so we need something that's really fast. Fourier methods can be really fast. But you have to upward continue to do your topography, and we just felt it really didn't fit with our seismic model. So that left us with a couple other options. We can look at infinite cylinders using Gauss's flux theorem, or we can do the classic Talwani method. The Talwani method, as you can see, it's quite a long equation to deal with. So for this talk, I'm going to be showing you a derivation using the cylinders. The reason for that is that it's a lot easier to follow. So first, what are we doing? So we're doing what I would call a finite element method. There's been some discussion that maybe this is actually a discrete element method or something else altogether. But the general idea is if you take something like the Earth, you can break up the body into smaller elements of equivalent mass. And if you sum all those together by superposition, you'll arrive at the same net acceleration. So we're going to be using a Cartesian grid today. Since then, we've done Talwani method, so we can handle rectilinear grids. There's also the possibility of using triangular grids. You'll see that in talk number 8 today. The reason that we chose to use the Cartesian and rectilinear systems is, once again, we're using iconal equation seismic methods, and that's what those are compatible with. So for this talk, like I said, we're going to be looking at infinite cylinders, and this is sort of the theoretical basis for that. So if we take each of our square elements in our grid, turn them into a cylinder of equivalent area and density, then we create a Gaussian surface that's centered around that. By this flux theorem, we can parameterize it with the area, density, and the distance to the center of the element, and we can arrive at the gravitational acceleration. However, we're only interested in this talk in the vertical component, so we have to take the product of that and an obliquity factor to obtain that vertical component, and we arrive at this really simple equation right here. So for the rest of this talk, I'm going to replace this scaling factor, which is the dimensions of each element, just with 1 phi. So that's going to contain those scaling factors and the other scaling factors needed to get it into milligauss. So when we took that model and we looped over each of the gravity stations at the surface of a model, oh sorry, you can't see that, what we would expect to see in a model with no lateral variation would be a flat response. But what we actually get is this convex profile. Now the reason for that is the gravity stations on the edge are further away from the center of the mass of the model. So you actually are moving closer to the center of mass as you get to the center. And this is commonly known as the edge effect. You'll see commonly a method that's used is just extending the model edges and using a sliding, or not even a sliding window, but just extending the edges out really far. So for instance, GMSys extends the edges 35,000 kilometers. You'll see in the third talk today, they actually just had a model that was much larger than their gravity profile. The way we resolved this was with a sliding window. And in this case, we're going to take each point and we're going to do a sliding window that's equal to 2 times the model length. And what you wind up with when you implement that sliding window is the correct response, which is a flat profile. So we went ahead and took this, and now we're going to try to implement topography with this model. And what we did is the convention of assigning a density of 0 for air. And this one's pretty straightforward. When we run the model across this with the stations up here, of course, we're going to obtain the incorrect response. So what we need to do for each station is compute the number of null-valued elements below that station and then drop the station into the correct location. So that's given by this value b right here. And in this case, we're using a vertical sliding window. And the vertical sliding window has a height equal to the height of the model. And when we implemented that, we obtained the correct response. So next, we wanted to look at a realistic model and kind of put this to the test with actual data that we might be looking at. This is the San Emilio Line 6 density model. It's a forward model found in Teplo et al. 2011. And what happened when I put this model into this density model into our gravity model is we wound up with these singularities. And we realized these occurred at each topographic step. Now, at this point, I began to question whether there was something wrong with our model, our gravity model. But the reality is the physics of our model were correct. The problem was that we built our model out of Legos. So each one of these steps actually corresponds to a 50-foot cliff in our model. And we know at San Emilio that there's no 50-foot cliffs. It's actually very smooth. So this led us to our next correction. And this slide is a little hard to follow, so try and stay with me. The first thing we're going to do to resolve this problem is we're going to calculate this value ZDC. It starts at 0 and it increments linearly to unity at the base of each topographic step. So you can see it scales up each time. We then multiply this factor by the height of that topographic step. And then at each station along the surface, we add that to the height, the elevation. What you wind up with is a correction that looks like this. We add that correction to the previous model, and you can see that it has the effect of removing those singularities. Now, this looks pretty good. However, when we zoomed in, we're going to zoom in on this element right here. What we found were there were still singularities at each step. Now, these are due to the missing mass below those stations when you move upward in the adjacent elements. The way that we solved this was pretty straightforward. We just applied a leapfrog smoothing kernel. Now, this smoothing kernel is centered on this element, and it's only applied to these 3 elements that have the singularity. So what you wind up with is a nice, smooth, monotonically increasing model as we expect. So you can see the changes sort of subtle. Okay, after we had this model in place, my next task was to make this model highly efficient. And when we dug into the framework of the model, what I realized was that for each station, or rather for all the stations, this part of the model doesn't change. So you can think of this as an impulse response. I like to think of it as maybe a Green's function, a geometry model. This part doesn't change. The only part that's going to change at each iteration in our optimization is the density model. And what this means is that we can take this part and we can store it into a vector. So this is what it looks like for the bottom of the model. Just to make it simple, I'm only showing you the bottom. So this is where a station would be located. And what we're looking at here is basically a plot of the contribution of each density element to the acceleration at that station. So as you would expect for a vertical component of gravity, it's sort of a cone that radiates outward from the station. You have very little contribution on the edges. And as I said, this is symmetric above and below. Remember, we're using that sliding window in the vertical direction as well. Now, the fact that this remains constant for every iteration means we only have to compute this one time at startup. We store that into an impulse response vector. Each time we update the density model, we store it into a density model vector that is compatible with our impulse response vector. And then we simply convolve those vectors. You may think of it as just a dot product. It's a very similar operation. And what we get is the gravity model at all stations. So what we found, just doing 1,000 forward models, we had a savings in computation of almost 50% or more than 50%. And this savings is only going to increase with increasing number of models. So for some of our optimizations, we may be doing up to 1 million iterations. And that's when you're really going to see the benefit of this. We wanted to validate our model against a really well-known technique. So we chose the Talwani method. You'll see this used a lot. What you're looking at here is a composite plot of 3 different gravity profiles. So first, red is this uppermost dike from 0 to 500 feet depth. And then yellow corresponds to the second one and blue to the bottom. Overprinted on those is the corresponding profile calculated by the Talwani method. And you can see our RMS errors are on the order of microgauss, which is within the error of our measurements in the first place. So we felt this was a very acceptable error. This is a look at comparing our model with the GMSys package. You can see that the fit is very good. There is a little bit of deviation on the order of 0.2 milligauss. We felt this was also very acceptable given that the models aren't actually the same. So GMSys doesn't use that finite grid like we do. So we felt that our model was validated. I just want to talk about the applicability of this method. So I've presented the simple cylinders method. Some of you may be wondering why I did the cylinders. We have done this with Talwani. That's what we're using now. You could also do this with Gaussian quadrature. So that provides an arbitrary level of precision. You only need to calculate it once up front. So if you need a very highly precise linear gravity model, you could turn to that method. But it just provides a level of precision that we don't really need for our purposes. And this method can be applied to any linear finite element method. That includes moving into 3 dimensions. So in conclusions, I showed you how we remedied the edge effects using a sliding window. We included topography with null densities and dropping the station into position. We resolved the discretized topography artifacts that are created by the discretized nature of our model. We then implemented a convolution operator, and I showed how it greatly reduces computation costs. This is my contact if you are interested in anything about this method. And this is some early results we have just doing a gravity optimization. So remember, I'm going to try to do a joint optimization. So I did a gravity optimization using simulated annealing. I like this figure. It kind of shows the non-uniqueness of the technique. And I've also created a seismic forward model. So now we're sort of playing with the joint optimization framework and trying to achieve a convergent optimization. And with that, if you have any questions, I would be happy to answer them.
We have plenty of time for questions, so if you have any questions, step up to the microphone, please.
Okay. All right, thank you.
Oh, is there a question?
Oh.
Yeah.
This is Hongzu from University of Utah. So in your conclusion, I see a slide you show that you inverted gravity data, you simulated annealing, is that right?
Simulated annealing? Yes.
So from what I'm seeing that your gravity field profile show is very symmetrical in left and right side, right? Can you show that slide?
Excuse me. Could you please close to the mic?
Yeah. So can you show that slide for the conclusion?
This one?
Yeah.
Yes.
So how do you confident about your inversion result? Because this model you see is very simple, right? And you get very simple anomaly. But your inversion, you shoot some very complex structure.
Yes, so I've put in a very complex structure. For instance, I've done the optimization for this profile. And what I found happened with this profile is about half the model over here has random blocks, and this side has almost nothing. So trying to invert this profile is really not effective. And that's where I'm hoping bringing the seismic in. The seismic will be more sensitive to the vertical contrast, and this will hopefully help guide the horizontal contrast.
All right, I see.
Yeah, so it's so non-unique. I tried doing some stochastic modeling, so I did a bunch of, basically hundreds of simulated annealing runs on this model, and you basically wind up with a blob of density on the right side and a lack of density on the left side. So we really, to do an inversion, I would have to do some form of regularization. I'm hoping the seismic will help achieve that for me.
Yeah, thank you.
Yeah, thank you.
Any other questions? In that case, the next talk will be in about 8 minutes or so from now at 8:55.
All right, thank you.